Hello everyone, my name is Siddeshwar Raghavan and today I would be presenting our work, Online Class Incremental Learning for Real-World Food Image Classification. Food image classification is a computer vision task that assigns a label to an input food image. This falls under the umbrella of food image classification, where deep learning models are trained to recognize different food items based on their visual features. However, in the real world, data is rapidly evolving with new categories of foods continuously being encountered over time. These classification models, trained from static data sets, are not representative of the real world conditions and lack the ability to adapt to sequentially presented data. It is always not viable to retrain the classification models as new food images appear, as it is computationally expensive and we may not have the resources to do so. Online class incremental learning is a machine learning paradigm where a model is trained sequentially in an online manner, meaning it continuously learns from new data as it becomes available in a single epoch without revisiting the older data. This is particularly relevant in the real world as data often arrive continuously and change over time, allowing the model to stay updated and representative of the conditions. The dataset is usually split into multiple tasks of sequentially appearing data and fed to the model for training. After a particular task is finished training, the model is tested on all previously learned tasks data. So as seen in the picture, as the model finishes the online learning task 1, it is tested on all images of or all categories of that task. And when task 2 is finished, it is tested on both task 1 and task two's data. In this work, we focus on a specific kind of online class incremental learning method called as experience replay, wherein a small subset of learned task data is stored in a buffer for knowledge rehearsal of older data to mitigate catastrophic forgetting. Most existing online class incremental learning methods assume that the distribution of the encountered data is perfectly balanced, which rarely happens in real world scenarios. Other commonly encountered constraints include balanced task sizes, balanced sample distributions, and disjoint categories across tasks. Motivated by this, we introduce a constraint-free probabilistic framework to simulate realistic food consumption patterns learnable in the OCIL setting, as represented by this figure, where we have overlap of categories across tasks and varied sample distribution and also varying task sizes. First, we present the realistic data distribution model to simulate food consumption patterns. Due to the unavailability of such food consumption patterns or data set to represent them, we end up simulating them. Nonetheless, considering the multitude of potential permutations in food consumption patterns, replicating every single one is a difficult task. To streamline this process, we classify the various food consumption patterns into three categories, which is short term, moderate term, and long term, aligned with the nutritional guidelines, reflecting the sustainability of diets over different time spans. To simulate such patterns, we propose a flexible framework based on three characteristics as shown on the right side figure. The first characteristic is the total number of classes in a task isn't fixed. Sample sizes of classes in a task may not be equal, and classes across tasks can overlap. Additionally, we also introduce two hyperparameters alpha and beta to control the degree of overlap and the degree of introducing new classes following any desired data distribution. To tackle realistic data appearances, we introduce a pluggable dynamic model update that can be attached to any existing experience replay online class incremental learning method. Our method focuses on the training pipeline without altering the exemplar storage and the retrieval mechanism and works in accordance with the method that it is attached to. As realistic data streams can contain repetitions and sample imbalances, it is essential to be aware of the input. To achieve this, we construct two virtual branches. The models used in these virtual branches are identical to the main model, trained up to the previous task. The weights in these virtual branches are frozen and are not updated using backpropagation. In branch 1, we infer the performance of the entire input training batch in a task. Branch 2 infers the performance of only the new data, which is the non-overlapped categories. We do this to avoid overfitting the model with classes learned sufficiently due to possible repetitions. The threshold to compare these branches against are set as the accuracy from the first task. The branch with better accuracy is propagated to the main model for training and subsequently to the buffer update modules. We compare the average accuracy of four most representative online class incremental methods for our experiments in the realistic food consumption patterns simulated, along with the addition of our proposed dynamic model update. We use a ResNet 18 backbone, which is trained from scratch. In these graphs, we represent the moderate food consumption category with a task size of 10 and a buffer of 2k. Graph A presents the comparison against each of the methods along with the addition of our dynamic model update module. Graph B shows how our method performs while changing data distributions when we are simulating these food consumption patterns. Similarly, it is also tested in the moderate um, classification category with 10 tasks. And we only use DVC for the experiment while varying distributions, as this was the best performing method when we made a comparison across all the online class incremental learning methods. We showcase that our method is robust to these changes in task sizes and distributions and boosts performance of existing methods in these realistic scenarios. To conclude, in this work, we introduce a probabilistic framework to simulate real-world food consumption patterns. Additionally, we proposed a dynamic model update, which is a pluggable module, as a benchmark for online class incremental learning in real-world situations. For future work, we would be focusing on exemplar storage procedures by exploiting the most representative samples simulated by our framework and evaluate our method on large supervised open world datasets. Thank you.